Okay, we're back to page 2. Looking at question number 9. We have an energy question. As a student walks downhill at constant speed, his gravitational potential energy does what? And if you read all the choices, there's actually also something about kinetic energy in there. Let's step back and talk about energy for a second. You have learned about 4 different types of energy this year. Kinetic energy, gravitational potential energy, elastic potential energy, or spring potential energy as we call it sometimes, and thermal energy. We're asking about 2 of those here. Okay, let's talk about the kinetic energy part first, because usually that seems to be the easier one for people. Kinetic energy, okay, the equation for kinetic energy, the symbol is Ke, is 1/2, the equation is 1/2 mv squared, m standing for mass, v standing for velocity. Or really speed, because kinetic energy itself is a scalar. We don't care necessarily which way something is moving, we just care that it is moving, okay? So, student walks downhill at constant speed. The downhill part has nothing to do with this. Downhill does not have anything to do with mass or speed or velocity per se. It tells us right here at constant speed, meaning v does not change. Their mass is also not changing. So that means the kinetic energy must remain the same. So that means we're only left with 2 and 4 as choices. The kinetic energy cannot increase. 2 or 4 are the only choices that have kinetic energy remaining the same. Student walks downhill. We want to know how that changes the gravitational potential energy. We remember that the gravitational potential energy equation, PEG, is mgh. M is mass, g is acceleration due to gravity, h is height. If they're moving downhill, they are losing height. Therefore, their gravitational potential energy must be decreasing. Okay? Energy questions, you sometimes really do have to break them down, answer them step by step. I know of at least one student that when they looked at this, they went way too far. They tried using conservation of energy. They said if they're going downhill, the speed must be increasing. Didn't even read this part. So you really have to read this stuff. Moving on to number 10. When 150 joules of work is done on a system by an external force of 15 newtons in 20 seconds, the total energy of that system increases by, that's a lot of words and a lot of numbers to deal with, and they even put these all in scientific notation. That's typically something that you guys don't really like. However, it takes about 2 seconds to get these out of scientific notation. Everyone should know what 10 squared is. It's 100. 1.5 times 100, that's 150. 2 times 100, 200. 3 times 100 is 300. And then 10 times 10 times 10, or 10 to the third, that is 1,000. 2.3 times 1,000 is 2,300. Okay? If it's easy numbers like this, get your answers out of scientific notation, okay? Don't do it for something like this, okay, where you have, well, I guess for this, 10 to the negative 8. That's just wasting time writing zeros. Don't do it for something like this, 10 to the 18th. You're just wasting time writing zeros. If it's a number you can easily write in standard notation, go for it, do it, if it makes you more comfortable. You can leave it in scientific notation too, but I know some people struggle with that. Anyways, back to the question. When 150 joules of work is done, so we're talking about work being done on a system. That word right there, work. There's a definition for work. And when I say definition, I'm talking about a word definition right now. The definition of work is a change in energy. If you do work, you are changing the energy of something. So when it says 150 joules of work is done, that means the energy of this object changes by 150 joules. Well, wait a second. The total energy of that system increases by. Isn't that talking about a change in energy? It absolutely 100% is. They are telling you the answer right here. This is the connection that they want you to get. The work is the change in energy. If you don't know that, you don't have much of a shot at this problem. But if you know that work is the change in energy, and as in 150 joules of work is done on a system, that means the energy of that system changes by 150 joules. And in this case, since it's work done on a system, the energy is going to go up. It's going to increase. So 150 joules of work is done, total energy increases by 150 joules as well. Okay? Very, very straightforward if you know that definition, which is why we spent so much time on it. 11, a person on a ledge. By the way, this is, I think, the hardest question conceptually because it focuses on a very specific fact, which probably not a lot of people remember. A person on a ledge throws a ball vertically downward, striking the ground below the ledge with 200 joules of kinetic energy. The person then throws an identical ball vertically upward at the same initial speed from the same point. What is the kinetic energy of the second ball when it hits the ground? So I'm going to draw a little picture here. Here's our ledge. Here's a person. They throw a ball. First, they throw a ball downward. And then the second time, they throw the ball upward. And it comes down. And the key thing is the velocity that they throw the ball downward with in the first trial is the same as the velocity that they throw the ball upward with. And here's the key fact that you can use in order to make this problem a lot easier on yourself. Okay? I'm going to erase this for just a second. When you throw something up, it comes back down. Let's say you want to know the speed at this point and the speed at that point. Okay? You can do the math on this. It's going to take me too long to do the math, so I'm going to skip it. But you can do the math and prove to yourself that the speed at this point when the ball is released and on its way up is the same as the speed when it gets back to the same point on its way back down. The only difference is in the direction of travel. Right now the ball is going up. Over here, the object or ball or whatever it is going down. But that's a key fact. The speed is the same if you're at the same height. Okay? So that means the speed is the same here and here, and here and here. The speeds are the same at all of those locations. So if I take this tennis ball and I toss it up, if I had a readout of the speeds in the y direction for all the different heights, we would see that the speed is the same at all the different, if we have 2 points that are at the same height, the speed on the way up is equal to the speed on the way down. Just the direction is different. So the velocities are essentially the negatives of each other. Now how does that help here? Person throws a ball vertically downward first. The person then throws the ball vertically upward at the same initial speed as before from the same point. So what that means is they threw it downward with some speed, then they threw the ball upward with some speed. When that second ball gets back to its initial spot, it's going to have the same downward velocity, the same speed, going the same, it's moving as fast as the first try. So really there's no difference between these two trials. It's just that one ball happened to go up first and then back down. Again, you can prove the math on this yourself. So if both balls, when they pass the person on their way down, have the same initial speed, have the same speed at that point, they're going to hit the ground with the same kinetic energy. First ball hit the ground with 200 joules of kinetic energy. The second ball is going to do the exact same thing. Okay? I think that conceptually is the hardest question that is on this test, at least in the multiple choice. Okay? I see when I took my first look at that, I was like, that is a pretty high level, in my opinion, for a Regents question. 12 and 13. So we have two construction cranes that are used to lift vertical 1,200 kilogram loads of bricks. I'm just going to start marking. I know that this is M, that's the mass, the same vertical distance, okay? So that the distance part, we'll call that D. The first crane lifts the bricks in 20 seconds, that's a time. The second crane lifts the bricks in 40 seconds, that's also a time. You could write T1 and T2 if you really want to. Compared to the power developed by the first crane, the power developed by the second crane is the same, twice as great, half as great, or 4 times as great. So we're looking for power here, and we need to somehow put it in terms of this, which it looks a little strange at first, but we'll get through it, okay? Let's think about power, okay? We know that power is equal to, from reference tables, the amount of work done divided by time. It's the rate at which work gets done. And work, we know, is the change in energy. There was a question, I think 2 or 3 questions ago, about how work is equal to the change in energy. We need to talk about what type of energy is changing here, okay, as the crane lifts up. Now, a lot of people will say, well, it wasn't the bricks or whatever this is, It wasn't moving initially, and then during the motion it is moving, so you're changing the kinetic energy. Okay, yes, but you don't necessarily know how much the kinetic energy is changing by. It's also very reasonable to assume that the bricks had a very, very short acceleration period, and then were at constant speed almost the whole way up, in which case the kinetic energy wouldn't change for most of it. So I'm going to actually ignore kinetic energy here, okay? Yes, it is technically true the kinetic energy changes, but we don't have enough information to say how it changes. We don't even know the distance over which this thing is moving, so we don't necessarily know how the kinetic energy is going to change. But what we can say with certainty is that the potential energy, the gravitational potential energy, does change. Okay, so I'm going to write change, that's delta, P-E-G over T. Gravitational potential energy equation is mg, and then the thing that's changing is h over time. That is equal to power. Just put my power. Okay. Now let's see here. We know that they are identical loads of bricks, so the mass is the same for both. Acceleration due to gravity should be the same for both. They're getting lifted the same distance. Now notice, even though we don't know that distance, we do know that it's the same. So we know that the work being done by both cranes is the same. The top is going to be the same. The only difference is in the times. First crane lifts it in 20 seconds. Second crane lifts it in 40 seconds. Bigger time. Now, if you were to take a number and then divide it by 20, and take that same number and divide by 40, what you would find is that dividing by 40 means that the power is only going to be half as great. Try it out, make up your own numbers. You'll see that that is the case. The power for the second crane is only half as great. Moving on to 13. An ionized calcium atom has a charge of plus 2 elementary charges. If this ion is accelerated through a potential difference of 2 times 10 to the third volts, in case you're nervous about scientific notation, that's 2,000 volts, the ion's change in kinetic energy will be what? And notice that we're in units of electron volts here. Electron volts make it so that it's actually very easy to do this question. Okay? Now, we're looking for change in kinetic energy. Just like question 12, just like question 10, change in energy means work. We're looking for how much work is done. And there is an equation in our reference tables. Okay, so we know this is a voltage. We know that this plus 2 elementary charges, that's a charge, that's Q. We know an equation in our reference tables that relates the voltage, or the potential difference, if you want to call it that, the work done, and the charge. That equation is this. V equals W over Q. All we have to do is plug in and solve. Let's see, change in kinetic energy. So we know this, 2,000 volts. Don't worry too much yet about this being in elementary charges, because we know that the charge, that's just going to be plus 2E, meaning elementary charges. We're going to end up multiplying these together to find W. 4,000, and then look at the units. We have an E and a V, and they're getting multiplied together. Well, that looks a lot like an electron volt. And as I look at all my answers, I see that that must be number 4. Okay? So what this is saying, because I just did a bunch of math there. What this really means is you take a charge, okay, and you put it through a potential difference, that is going to change the energy of the charge. You are accelerating it through a certain potential difference. Based on how big that potential difference is, and based on how big the charge is, you can actually figure out how much energy it's going to gain. In this case, 4,000 electron volts. Okay, so let's erase this and move up to the other side. See if I can get the next 5 done relatively quickly. Okay, a total charge of 100 coulombs flows past a fixed point in a circuit every 500 seconds. What is the current at this point in the circuit? Well, current we know is just a movement of charge, a flow of charge. Current is symbolized by I. We know how much charge is flowing past in a certain amount of time. This is a very straightforward equation from the reference tables. The definition of current is the amount, and don't get really thrown off by this delta, it just is there to symbolize charges flowing. The change in current, or the flow of current, over how much time it takes. So we have 100 coulombs divided by 500 seconds. We are left with 0.2 amps. Remember, an amp is a coulomb per second. It's a unit of how much charge is flowing past per second. That is I. That is choice number 1. Okay. All right, 15, another electricity question. An aluminum wire of length 1 meter has a resistance of 9 times 10 to the third, negative third ohms. If the wire were cut into 2 equal lengths, each length would have a resistance of what? We spent some time talking about the resistance of a piece of wire as opposed to just a resistor. The equation given for that is R, and it doesn't say this in the reference tables, but R wire, resistance of a wire, equals rho, which is resistivity, times L over A. Resistivity is a property of the material, okay? I'm assuming if we're cutting the wire in two, we still have the same material. So this is not going to change. The cross-sectional area, that would be like if I took this marker and sliced it in half and you looked at the newly exposed face, that would be the cross-sectional area. Me just slicing a wire is not going to change the cross-sectional area. So that stays the same. But I'm cutting the wire into 2 equal lengths. In other words, I'm reducing L. So the first thing I need to figure out is which one of these, or which one, if I'm reducing L, that should reduce the resistance of the wire. Are any of these bigger than the original resistance? Be careful with the scientific notation. This one is bigger than the original resistance. This is the same as the original resistance. Can't be either of those two. I'm left with 1 and 2. Okay? I'm cutting something in half. That means L is half as big as before. If this equation is still to hold true, and rho and A don't change, our wire must also be half as big. And half of 9 times 10 to the third ohm would be 4.5 times 10 to the negative third ohm. Okay? 16, 17, and 18. In an operating electric circuit, the source of potential difference could be, this is worded a little strange, okay? The source of the potential difference. What this really means is what is actually putting energy into the circuit. What puts energy into the circuit? The source of the potential difference, the thing causing there to be a difference in potential. In other words, causing it to make it so that electrons at one spot are giving up their energy as they pass through something else. If you have a circuit without a source of potential difference, the electrons aren't going to move around. You need something to give them that energy. That thing would be a battery. Okay, this is pretty straightforward once you understand what it's asking. It's not asking what. It's not asking where the electrons give up their energy. It's asking what gives them that energy that they carry with them in the first place. A voltmeter doesn't do that. A voltmeter just simply measures the potential difference. It's not the source of potential difference. It helps you measure it. An ammeter measures current. That has nothing to do with this. A resistor is where there is a potential difference, but it's where energy is being given up, not where energy is given to the charges. That's a little tricky wording, but I hope you understand why the answer is to a battery. The question is really asking what puts energy into a circuit, and a battery is a power source or energy source. 17, this is a pretty straightforward calculation question. A light bulb with a resistance of 2.9 ohms is operated using a 1.5 volt battery. At what rate is electrical energy transformed in the light bulb? When you see something about electrical energy and rate, please remember that we are talking about power here. Okay? The rate of energy being used, or rate of energy in this case being transformed. So what we are looking at here is we are told the resistance and we are told the voltage, the potential difference. This is why I write these things down. This is why I look specifically for what they are giving me. Because otherwise, there's a whole bunch of equations for power. You need to pick which one is best. In this case, they are telling you the voltage and the resistance, the potential difference in the resistance. The equation for power that involves both of these things, if you look in the reference tables, is V squared over R. All we need to do is plug these in. 1.5 volts squared over 2.9 ohms. The power ends up being equal to 0.78 watts. Very straightforward, but you really should be familiar with those equations, or at the very least, be writing them out and using the reference table. And again, energy being transformed is power. The last question is another question that's fairly straightforward once you understand what is being asked. 18. A 40 kilogram child exerts a 100 Newton force on a 50 kilogram object. The magnitude of the force that the object exerts on the child is what? There's no calculation involved here, okay? Child exerts force on object, okay? Take out all the numbers, you get a child exerts a force on an object. The question is asking magnitude of force object exerts on child. So we're talking about two forces. The force an object puts on a child and the force that a child puts on an object. I've been training you all year for this. When you see this sort of language where you have two objects and you're being asked about the forces between those two objects, okay? When you're just taking the two objects and kind of flip-flopping their place in the sentence, that is a dead giveaway that we are now talking about Newton's third law, N3L. And Newton's third law says that every action has an equal and opposite reaction, meaning that this is a force pair. You have a child exerting a force on an object. The object exerts the same force back on the child. There's only one force that we're talking about here, the 100 Newton force from the child on the object. Therefore, the object must also exert a force of 100 newtons back on the child. There's questions 9 through 18 of 2019 Regents.